Hello, it's Stat 134, Lecture 30. Announcement, Quiz 7 next week is canceled. Too much stress. We got to keep you guys happy. Last time, we were covering section 5.2, and we learned how to find marginal density, which essentially is to find the marginal of y you are integrating out x. Section 5.3 on independent normal variables, we started. If x and y are IID standard normal with density phi of x is some constant e minus 1/2 x squared, where c is positive. We actually don't know yet what constant we need so that the standard normal will integrate to 1. It turns out to be 1 over square root of 2 pi, but we're going to actually show that today. So then the joint normal, because x and y are independent, is c squared e to the minus 1/2 x squared plus y squared. And remember that the shape of that is like a bell. It's like a Liberty Bell or something. It's radially symmetric, and we still need to show that the expectation of x is 0 and the SD of x is 1. Today we're going to first look at student explanations of the concept test from last time. We'll introduce the Rayleigh distribution, and we'll show that the sum of independent standard normal random variables is normal. So that's for today. Last time we had the concept test where s and t are IID exponential lambda. X is the min of s and t and y is the max. The joint density we showed was 2 lambda squared e to the lambda x plus y. And we were asked to find the marginal of x. And here's a nice explanation. The important part is that y goes from x to infinity because y represents the maximum. At that point, take the integral of the joint density with respect to x from x to infinity to get this answer. Another person writes, integrate the joint from x to infinity since y is greater than x. So that's all a nice explanation, and I've written out my solution below. So the Rayleigh distribution is a useful distribution to know for its own right, but it actually will tell us a lot about the normal distribution, as we'll see. So let t be exponential 1/2 and r to be the square root of t. So r is called the Rayleigh distribution. It's defined as the square root of exponential 1/2. And I asked you guys to use the change of variable formula to find the density of the Rayleigh distribution. So you did a change of variable, and that gave you the density r e to the minus 1/2 r squared for r greater than 0. So we can then find the CDF. So let's take a look at what the probability that r is greater than r is. So noting that because r is positive, this is equivalent to the event r squared is greater than r squared. So they'll have the same probability. And r squared is t, which is exponential 1/2. So we do know the survival function for t is e to the minus 1/2 t, which in this case, so it's greater than r squared. So minus 1/2 r squared in this case. So that is the probability that r is greater than r. So the CDF then is 1 minus that. So now, if x and y are IID standard normal, okay, what's also true is that the Rayleigh distribution is the square root of x squared plus y squared. And so this is something that you could show using a multivariate sorry, yeah, multivariate change of variable formula. Here, our transformation G is of two variables, x and y, but we're not going to do it that way. Instead, we're going to just look at this geometrically. So instead, let's let r be the square root of x squared plus y squared. What's the probability that r is in dr? So that's the volume of the cylinder under the joint normal over the shaded blue annulus shown on the left here. So so the probability that r is in dr is the height of the joint density above the blue annulus times the area of the blue annulus, and the height above is just given by the so it's given by the joint density formula. We have x, so in the blue annulus we have x squared plus y squared is r squared, and then the area of the blue annulus is 2 pi r dr. So I've tried to illustrate that here. If you just straighten out the blue annulus, its length is 2 pi r and its width is dr. So right, when you write this out, this has to be the density of r times dr, and we notice inside of it the Rayleigh density, which is r e to the minus 1/2 r squared. So actually we're going to conclude from this that c squared times 2 pi has to be 1. So let's see how that works, right? If you integrate the probability that r is in dr from r is 0 to r infinity, that has to integrate to 1, right? And so so you can integrate c squared times 2 pi r e to the minus 1/2 r squared dr. You can pull out the constant, and then you have the integral from 0 to infinity of r e to the minus 1/2 r squared dr. This is 1 because r e to the minus 1/2 r squared is a Rayleigh density. And so we conclude that c has to be 1 over the square root of 2 pi. So that's pretty cool. We've shown two things doing this. One, we've shown that if x and y are IID standard normals and t is exponential 1/2, that the Rayleigh random variable can be written two ways. One is the square root of x squared plus y squared, and also as the square root of t, which is how we initially defined it. So both of these are Rayleigh densities. In other words, that implies that x squared plus y squared has the same distribution as the 1/2, which remember is the same as gamma 1/1/2. So that tells us that x squared plus y squared is gamma 1/1/2, and that's quite interesting. Secondly, we learn what c is, right? We learn that c is 1 over square root of 2 pi. So now we have actually proven that the density of the standard normal is what's shown here. And then actually it's easy to show also that the expectation of x is 0 and the SD of x is 1. Very easy. I just included it at the end of the notes, so you can take a look at that. So then we did an example involving the Rayleigh distribution. So suppose 3 shots are fired at a target. Assume for each shot both x and y are standard normals. Let W be the closest distance among the 3 shots to the bullseye. Find the density of W. So W is the min of R1, R2, R3, and where these are IID Rayleigh. And right, so you can solve that here. So one way to do it is to use the CDF, and using the CDF, remember for min, the probability that W is greater than W is the probability that R1 is greater than W, the probability that R2 is greater than W, the probability that R3 is greater than W, which is probably that by independence we have probability of R1 greater than W cubed, which we know that that's e to the minus 1/2 W squared cubed, so that's e to the minus 3/2 W squared, and that means that the CDF is 1 minus that, and you can take the derivative to get the density. So some of you also used, thought of W as a Rayleigh ordered statistic, and did it the way that we've done it. We've done those type of calculations, and I'll write out the solution that way, and I'll post it in the lecture notes. So the sum of independent standard normals is the next topic. So we need to know two things. One is that when you transform your random variable by just doing a rigid motion of essentially flipping it across the y-axis, so transforming x to minus x, it has no effect on the density. The density remains the same. So fy of y is equal to fx of x. There's no stretching in that case. So 1 over the absolute value of the derivative of g is just 1. Secondly, a rotation matrix is what's shown here. It takes 1, 0 to cosine theta, sine theta. It's rotation by theta, has this form. Rotation by minus theta has the form cosine theta, sine theta minus sine theta, cosine theta. And linear combinations of rotations is the next topic. So we're going to show that if you add two independent standard normals, you'll get a normal. So first we're going to show that if x and y are IID standard normal, then the cosine of x plus the sine of y is standard normal. So this is very easy to show. If x and y are IID, xy is a point on the plane, and here's the joint normal. And let's look at the point given by rotation of xy clockwise by minus theta. So here's a picture, and that takes us to x theta, y theta. I want to know what's the joint density of x theta, y theta. So in fact it has exactly the same joint density as xy, because all we're doing is a rigid motion. So this is a rigid motion in the plane, and a rigid motion in the plane is either a rotation or a reflection. You could use a multivariate change of variable formula here to show that the density is the same, but we're not going to do it that way. For those of you that know multivariate calculus, essentially what's happening here is that the determinant of the Jacobian is plus or minus 1 here, and so the absolute value of that is 1, and that's why it's not changing. There's no stretching. So we get the joint density is 1 over 2 pi e to the minus 1/2 x squared plus x theta squared plus y theta squared, and you can compute the marginal density and easily show that the marginal x and y is standard normal. So that shows that. And now how can we write x theta as a function of x and y? Well, we're rotating x theta, y theta is the rotation of x and y by minus theta. So I'm just going to apply that rotation matrix, and you see that x theta is cosine theta x plus sine theta x. The reason I'm using a rotation by minus theta instead of plus state is because